Let's pick up our conversation of psychology and scientific thinking by talking about pseudoscience. Can a bump on the back of your head offer a clue to your inner personality? That sounds a little crazy, but this idea was a central theme in phrenology, a type of pseudoscience that involved linking bumps on a person's skull to certain aspects of the individual's personality and character. Let's learn a bit more about phrenology and we'll talk about how and why that is a form of pseudoscience.
A lot of exciting neuroscience was happening in 19th century England. Victorian scientists were figuring out that certain parts of our brains are connected with certain parts of our bodies, like different senses or muscles. But mixed in with the legitimate research was some pseudoscience, or misleading ideas that spread without rigorous scientific backing. Like one theory from Viennese physician Franz Joseph Gall, who thought that character traits like religiousness or curiosity were also linked to specific brain regions. This theory became the basis of phrenology, a field of study that claimed that you could determine someone's personality by the shape of their skull. Phrenologists believed that all human brains were made up of many distinct organs that could be mapped to various personality traits. They claimed that the more you used a certain brain region, the bigger it got, and the less you used it, the smaller it got, kind of like how muscles work. And they assumed that the skull conformed to the shape of the brain, revealing where these bigger and smaller organs were. So theoretically, you could inspect someone's skull to figure out parts of their personality. Phrenology became enormously popular in the UK around the early 1800s and spread to places like America, France, and Germany. It was pretty much a load of garbage and guesswork, and many scientists were vocal critics. But at the time, there wasn't enough evidence to thoroughly debunk the theory. Researchers would, of course, dissect the brains of dead people, not living people, and the human body changes a lot after death, so even if living brains were different shapes, dead brains probably looked pretty much the same. Plus, the public thought phrenology was really compelling. Just like horoscopes, people tend to love things that tell them something about themselves. So phrenology thrived on subjective validation, which is the idea that people tend to believe in something if it's personally true or meaningful for them. But as the ideas spread, they started being used to justify race and class inequalities. Upper classes used phrenology to reassure themselves that they were supposed to be on top because of the ideal shapes of their brains. The lower classes, on the other hand, accepted the pseudoscience because it claimed that these brain organs could be developed so they could improve themselves with hard work. The American physician Samuel Morton made even more sweeping claims about skull shape in a book, Crania Americana. Morton argued that Caucasians were superior to other races like Africans and Native Americans because of craniometry, or different skull and supposedly brain sizes, which is just racism under the guise of science. Some phrenologists used these ideas to rationalize slavery and colonization, while others were anti-slavery because they thought these inferior races ought to be protected. Eventually, all of this scientific racism was acknowledged, and phrenology's legitimacy took a nosedive in the mid-1800s as we continued to learn more about how the human brain actually works. First of all, the brain conforms to the shape of the skull, not the other way around. And secondly, the brain does not physically grow or shrink like our muscles. Phrenologists were also wrong that the brain was made up of discrete chunks. It's one organ with a bunch of networked cells. But there was something to the idea that the brain was spatially organized, and different regions were linked with different functions, which we call functional specialization. The French physician Paul Broca contributed some evidence to support this idea in the 1860s. He found that damage to the left frontal lobe in humans was linked to speech impairment without affecting someone's ability to understand what other people were saying. In the 1870s, Gustav Fritsch and J.L. Hitzig were experimenting with stimulating different parts of the cerebral cortex of a dog, which produced movement in different areas of its body. Through experiments like these, scientists were able to develop a better understanding of different regions of the brain by the start of the 20th century. Unlike phrenological maps, which assigned arbitrary brain areas to personality traits, our current brain maps are based on experiments that show different functions of each region. With the development of technologies like magnetic resonance imaging and computed tomography, and the ability to do careful brain surgery, our understanding of neuroscience continues to grow. Nowadays, we are positive that phrenology was junk science. The shape of someone's head doesn't say anything about their personality, character, or moral depth. But we can still see its echoes in language we use today, like highbrow, lowbrow, and well-rounded. Phrenology may have lacked scientific merit, and was definitely used to justify harmful ideas, but it did cause scientists to think more critically about how biology is intertwined with thoughts and emotions. Thanks for watching this episode of SciShow, brought to you by our patrons on Patreon. Now, how that works is
This guy's YouTube channel is awesome. If you're ever curious or looking for more information, I'll use a few of his videos throughout the semester, but I really like him. And he does a really good job of describing things. So we talked about phrenology. I also like that he started to talk about some of the different areas of the brain, a little bit of a preview for a few weeks from now when we're going to come back around to that. He also talked a bit about how phrenology is in fact a pseudoscience, and we debunked it using research. So we're going to talk a bit more today about pseudoscience, and then we'll talk more next week about how research can really help us to make sure that we are doing good, sound science. The word pseudoscience literally means fake science. Pseudo means fake, and science means science. Okay? What it is that pseudoscience really lacks the safeguards against bias that characterize real science. And so we have to really ask ourselves, how do we know when we're about to fall guilty to pseudoscience? There's a few red flags or warning signs that we can keep an eye out for. And the first is the overuse of ad hoc hypotheses. Sounds really fancy. Basically, what this means is that we tack a hypothesis on after the fact to keep our work from being falsified. Say someone was trying to convince you that leprechauns are real. No matter what you say, they can keep adding on ad hoc hypotheses that can't be falsified. Oh, well, they're invisible, they have complex motives, they only come out on St. Patrick's Day. Can't really do much with that, especially when you keep changing the story. Or a psychic might blame bad vibes as the reason that their claims of telepathy didn't hold up under scrutiny. It's really difficult to do too much with. Second is the lack of self-correction. As scientists, as humans, sometimes we're just wrong, right? We might spend years working on something only to later find out, nope, that's not actually how it really is. We have to be able to adapt and grow and change and keep an open mind to the fact that we may just be wrong. Unlike real science, though, pseudoscience rarely gets updated, even when new data or information come to light. Then there's the over-reliance on anecdotes. An anecdote is a story or something that you hear. It's not rooted in science. It's just kind of like, hey, this happened to me or to my cousin. You may have heard the idea that autism is caused by vaccines. Okay, so several years ago, a study came out showing a causal link between vaccinations and autism. So kids got vaccinated and it caused them to then develop autism. It was later revealed that that study was actually done using poor science. For reasons that we'll talk more about next week, but the gist is that the information that the researchers presented was not sound. Problem was that the idea had already taken root and it had already caught on and sort of spread pretty wildly. What started happening was that people were wary about vaccinating their children, or people who had vaccinated their children who then were diagnosed with autism were using that to further the claim. You may have heard someone say, oh, my friend's uncle's cousin's sister's monkey's best friend kid had got vaccinated and then that caused them to have autism. That's an anecdote. That's something that you're just hearing. Oh, well, my grandmother did this and blah, blah, blah. Another great example is the link between the COVID vaccination and any sort of problem outcomes. Oh, well, my mom got the COVID vaccine and then she got a rash. So the vaccine causes a rash, or we don't know that, right? So I'm not saying there's not a link. I'm not saying there's not something to consider there, but you can't just listen to one person's story and say that that is science. The thing is, going back to the autism example, maybe the friends, cousins, nephews, whatever, maybe this was a freak scenario where for that child in that context, that the vaccine did lead to them developing autism. Maybe, right? We can't say for sure. But the more likely scenario is think about when we get vaccinated versus when the warning signs for autism start to happen. It's right around the same time. So chances are good that that child was already autistic and they just happened to start noticing the patterns of behavior characteristics of autism around the same time that that the vaccination occurred. We don't know. Anecdotes don't let us say that for sure. They're also impossible to verify. We'll never know for sure what happened with the cousin's friend's nephew. So it's impossible for us to use that as scientific evidence. And so you may be wondering why we should care about pseudoscience, and hopefully the video we watched gives you a bit more background on that as well. Pseudoscience feels safe and easy and familiar. We're drawn to it because it just sort of it feels easy, but it can be really dangerous. There is absolutely not a shred of scientific evidence to suggest that vaccines cause autism. Yet people hear these stories and use them to make medical decisions for their children. I mean, that's really quite problematic. Or you thinking about phrenology, how it was used to justify things like racism. So, in short, let's avoid pseudoscience. Let's try our hardest to stick with real, objective, replicable, or repeatable science. This means that we are going to have to be scientifically skeptical. We have to evaluate claims with an open mind. We have to have a willingness to accept claims only after they've been subjected to careful and rigorous scientific testing. Just because it's online, just because they said it on TV, doesn't mean that it's true. Even if it's said by somebody who looks very official wearing a lab coat, they're probably just an actor wearing a lab coat. The general gist here is to not accept things willy-nilly, to demand data, demand sound evidence. Look at your sources. For your assignments for my class, I ask you to use scientific sources to back up your answers. And I do this because not because I'm trying to be mean, but because I'm trying to force you to really think about where your information is coming from. And I will be very critical of the sources that you use. If it's just a blog page, well, who wrote that blog? Do they have the credentials? Do they have the expertise to be able to make that claim? So make sure just because you're citing a source doesn't mean that it's a good source. Ask, ask who wrote this paper? What are their credentials? What expertise do they have to speak on this area? And it's not just credentials, right? I have a doctorate degree in developmental psychology that gives me the authority to speak on developmental psychology. I don't know bupkis about chemistry, and I know even less about history, right? So just because you have the degree, that doesn't mean that you have expertise in every area. Think critically, right? Demand data, demand evidence. Now, there are six major principles that guide scientific critical thinking. Oh, whoops, I meant to put these up. Okay, we'll move on. There are six principles that guide scientific critical thinking. The first one is to rule out rival hypotheses. We haven't talked much about hypotheses yet. We will do that more next week. But a hypothesis is essentially an educated guess for what you think is going to happen. So here what we want to do is ask ourselves, are there any better ways to explain what could be happening? Think about a clinical trial where depressed people get a new medication and they improved more than the equally depressed people who did not get a medication. Okay, so one explanation is that the medication improved the symptoms of depression. Absolutely. But it's also possible and cannot be ruled out that people who got medication expected they'd feel better because they took something. Ever do that where you have a headache and you take a Motrin and you say, I'm going to feel better now because I just took something? That's real. That's known as the placebo effect. It's actually a very, very powerful effect. It's why clinical trials often involve giving a sugar pill or a placebo to the control group to make sure that we're ruling out the effects of simply consuming medication. We'll talk more about control groups next week. Another topic that we'll swing back to next week in research methods is correlation versus causation. I'm sure you've all heard this in some capacity or another. Research is concerned with the relationships between variables. Okay, variable that is anything that can vary: height, IQ, weight, loneliness, self-esteem, bullying. When we're thinking about the relationship between two variables, we often want to know, well, does variable A cause variable B? Sometimes. This is very difficult to establish, though, and it requires the use of specific research designs. Again, preview for next week. Correlation just means that there's a relationship between two variables. The social media and loneliness, we know that they're associated, but does social media cause us to feel more lonely? Or can we flip that around? Do lonely people seek out more time on social media? Right. So for now, suffice it to say that just because two variables are related does not mean that one causes the other. As scientists, we have to use the term cause very, very carefully. And then there's falsifiability. Karl Popper first suggested that for a claim to have credit or to be meaningful, we need to be able to show that it is false. If I were to make a hypothesis that the human spirit is based on our connection with nature, well, how do I test that, right? How do I show that to be true or show that to be false? I really can't do very much with that. But if I were to say that people who listen to classical music do better on a test than people who don't, well, I can do a test on that and it will either be supported. My prediction will either be supported. People in the classical music group will do better on the test than the other group. It won't be supported, right? Maybe the people in the no music group do better, or maybe they'll do exactly the same. But your claim has to be able to be tested and shown to be false. If you can't do that, it's not good science. It's not a good claim. Replicability. Okay, this is the idea that our results have to be able to be duplicated or copied. We use replicability to rule out freak findings. Consider, and I'm totally making this up just as an example, consider a study on music and vocabulary. Let's say there's 100 studies that show that babies who listen to classical music during their first few weeks of life show better vocabulary retention at age 4 compared to babies that don't listen to music. Then there's one study that shows that listening to classical music is associated with worse later vocabulary retention. Well, that one study doesn't hold much weight because it hasn't been duplicated consistently. When you run a study, you need to be able to run that study multiple times and have the results come out the same. Otherwise, what good is your research if you can't replicate or get your results again? We're actually in something called the replication crisis right now. What we're finding is that many studies that have been published in some of our biggest and strongest journals actually can't be replicated. When we try to run them again, we get different results. That's a pretty big problem. And so there's some things that we're doing about it. Actually, Brian Nosek is doing some really cool work in this area if that's something you're interested in. One option is to pre-register your work. So to sort of say before you even get started, here's what I'm doing, here's what I think I'm going to find. It's an accountability thing. We're also trying to replicate more studies instead of just accepting that one study that was published one time. Can we get the result again? Extraordinary claims. Is the evidence as convincing as it claims to be? Someone claiming they saw the Loch Ness monster would need to have some gosh darn compelling evidence to that effect in order to establish any credit towards getting people to believe them. So whenever we're evaluating a claim, we should consider whether the claim runs counter to things we already know. If so, we should ask ourselves whether the evidence is as extraordinary as the claim itself. And finally, Occam's razor refers to simplicity. You may also hear this called parsimony. I always think it's a little funny that the critical thinking principle that refers to simplicity has a really complicated name. When we're thinking of a hypothesis to explain why or how something happens, sometimes the simplest explanation is the best. In the 70s and 80s, farmers started to see crop circles appearing in fields. They were really baffled. What are these perfect circles that are showing up? And so they offered a hypothesis for why those crop circles existed and where they came from. Aliens, it must be aliens. Obviously, it's aliens. I mean, okay, we can roll with that as a hypothesis. Question whether it's falsifiable, but let's roll with it for a second. It turned out, upon further investigation, that crop circles were being created as pranks by a couple kids. Um, in summary, when we are confronted with two explanations that fit the evidence, it could be aliens, it could be feisty teenagers choose the simpler option. In our next unit for this week, we're going to take a crash course through the history of psychology. We're going to think about where the field is today, what are the things that are important to the field today, but also where do we come from and how did we get here? So I'll see you then.